continue the topic of optimization, and let's do a real fast recap of the material that we had before. We talked about the convex set. We start with affine sets. We define the convex sets. Line segment was all points between 2 point x1 and x2, and where the theta is some number between 0 and 1, and we define a convex set as this one. Let's go a little faster. We define about the convex hull and convex combinations. We had the set of the points, and we define this gray set as a convex hull, and if we have the original sets as this one, the gray one is the convex hull of this set. And we define the convex cone as follows. If you have 2 points, the points that they are between these 2 points, where the theta 1 and theta 2 are bigger than 0, creates a convex cone. We talk about the half space and hyperplanes, and then goes to the Euclidean balls and ellipsoids, and talk about their properties. We talk a little about the norms ball and norm cone, and polyhedra, which is the area that can be defined by some quality and inequalities. Then we define the positive semi-definite cone, and after that we went to the operations that preserve the convexity. For the operation that will preserve the convexity, we use the 3 methods. First one, we can apply the definition of that. Second one, we have some operations that can preserve the convexity, and the third one that we talked about, it was the MATLAB function that we can start to pick some points and see if the line between these points are in the set or not. And yes, in the operation that preserves convexity, we have intersection, affine function, perspective function, and linear fractional function. That's yes. The first one is the intersection. If we have two convex sets, the intersection of this convex set are convex. Then we went through the affine function and perspective function. We prove some of these properties, and we talked about the generalized inequalities, and minimum element and minimal element, and the supporting hyperplane, dual cone. Yes, and we last meeting we had some talk about the convex functions, and we start with the basic properties and some examples. The definition of the convex function, we can define a function from Rn to R is convex if first the domain of the f is the convex set, and if we have this property, if f of theta x plus 1 minus theta y is less than theta fx plus 1 minus theta fy. And if you want to draw a picture, this is the picture, this is the function. This is our function, and this is first point. The point x and fx and y and fy, and if we draw a line, the value of the function is less than equal to the value of this combination of theta x1 and 1 minus theta f1. We had some example in the real numbers, affine function, exponential function, power, absolute values, negative entropy x, log x, that in continue we will talk about that and prove some of these properties. And concave function, it can be affine function, power if the power is less between 1 and 0, and logarithm can be one of the concave functions. Okay. One thing that we talk about that the restriction of the convex function to a line. If we have a function that we can restrict it to the line and it's still convex, the function is convex for if this restriction can be done for any given line. We had some example and we proved the properties, and we talked about the extended value extension. Extended value extension, if we have a function, if the function is, let's say we have something like this as a function, and the domain of the function is from here to here. If we wanna have if we call this function f, we can have the value of plus infinity if the x is not in the domain, we have the value of plus infinity for the function. Okay. Yes. And we talked about the first order condition. It was very fast, and yes. For the first order condition, we have fy is less than fx plus the first derivation of fx on the point multiplied the y minus x for all xy is in the domain. I think I didn't do any proof for that. Only we talked about that this is the underestimator of the function. On each point, if the function is convex, always this value is less than the original value of the function f. Let's see how I can find it twice. their definition that says fy is bigger than equal to fx plus y of x y minus x. For a theta between for a t between 0 and 1,
This is if y minus x or y minus x. Last sentence is f of x, y minus x.
for a t between 0 and 1, f of x plus t y minus x is less than equal to y minus t f of x plus t we can move the fy to
Parenthesis.
I missed one.
This parenthesis for the rest.
It really is to a little more pressure. And it's I can move fy to this side, put the others here, and divide by t, and we will have fy is bigger than equal to f of x plus f of x plus t y minus x minus f of x divided by t, and if t goes to 0, this will give us this definition. It's the it's the value of the derivation in the point y minus x and it's the same as this one. Okay.
So for the second equation, I think it should be, if the parenthesis should be the last.
I missed the parenthesis.
Yeah, the second row.
Yes.
Yeah? That's third one.
It's f of x plus t y it's same as 1 minus tx plus ty, and then we can use the convexity rule that says, for example, this one is less than this value, then we move fy to this side, and if t goes to the 0, this one is equal to fx because this one is a 0 and 1 fx plus this term here. Even we can have it, we can divide into two parts, keep the 1 fx minus tfx and tfx from here, and we have 1 t here, it can be cancelled, and we have fx plus t, this one, which is the definition of the derivation in the point y minus x. Yes. Okay. It is the first order condition. For the second order condition, the function is supposed to be twice differentiable, and the Hessian of the function, if it's available, it's supposed to be positive if it's supposed to be positive semi-definite, because it's not the number that be positive is can be the matrix, and the matrix is supposed to be positive semi-definite, and if it's positive definite, the function of f is strictly convex. Okay, let's start some examples. First example is the quadratic function. It's 1 over 2 x transpose px plus q t x plus r. That the first order derivative of fx is px plus q, and the second order is only p. It means if p is positive semi-definite, the function of fx is positive semi-definite. The next example is list square objective. In the list square objective, we have fx is norm square, norm 2 square of the ax minus b, and the first order derivation is 2A transpose multiplied this function, and if you want to do the second one, it's 2A transpose A, and here it's convex if it's convex for any A, because it's a quadratic term and it's always positive semi-definite. And for quadratic over linear, we have a function of f x y is equal to x squared over y, and if you want, I can work out how we can reach to this definition. Erase all of it. Okay. I want to find the original function is equal to we want to find this matrix. Okay, let's see what's root f around x. This one is 2x y, and root f root y is equal to okay. X squared minus and you need double twice derivation of the function. If we do the derivation of the y, it will be equal to if you want to do the I can have a factor of 2 over by 3, and the matrix inside is y squared minus x y minus x y. This one is equal to okay, and if this function, if you want to have this function be convex, this Hessian function is supposed to be positive, and we know this term is a quadratic term and it's always positive, but for having whole thing positive, the y is supposed to be bigger than 0. If y is bigger than 0, this function is convex. And there's other type of the function. For example, we have a norm. I think I use the norm properties for same as this one for the for the norm, we define f from Rn to R, and for a theta between 0 and 1. I think it's obvious. For the norm, we have a triangular inequality that says if we have, for example, norm of a plus b is always bigger than, if I'm saying correct, bigger than, is less than norm of a plus norm of b. It's less than equal to the norm. It's the same as this one, it doesn't have anything. But for the max function, if you have a max f of theta x plus 1 minus theta y is equal to max for over I for theta xi plus 1 minus theta yi, and this one is less than equal to theta of max I of xi plus 1 minus theta max by y, which is equal to theta fx plus 1 minus theta fy. For the log sum of exponential, this function is convex. For proving it's convex, we need to calculate the derivation of xi, xj for each coefficient of x, and after calculating all of them, we can express it as this matrix term. This term is a quadratic and it's always positive, and for having this, we need to have some more steps to prove that this term is bigger than this term, and always this term is bigger than that one, and the log sum exponential is a convex function. But for the geometric means, this function is not convex and it's a concave function. Let's see, do I have any examples? Okay. Let's start with the new topic, which is the level set function. Level set function is the set of f from Rn to R, and we define it on the domain for the points that are in the domain of the f, where the value of the function is less than threshold alpha. And the sublevel function is a convex function. But if if the function is convex, the sublevel function of that function is convex. But if sublevel function of some function is convex, it doesn't necessarily to the original function be convex. Epigraph. Till now we talked about the sets and functions. Epigraph is the connection between these two topics. We define the convex sets and we define the convex function. Now, by defining the epigraph of the function f, it's the we can define as this one is the R point above the function, and if the function is convex, the epigraph set of the function is a convex set. And it's correct if epigraph of the function is convex, the original function is convex.
What is the epigraph?
Epigraph is
Epigraph is a set, or is it
it's this area. If you have a function f, the area above the function is the epigraph of the function.
What's the property of it? What's the property of the epigraph? How we can find that this, for example, this one is an epigraph. This one is a function.
For example, you have one function. This area is epigraph of the function. If it's the way that you can prove that the function is convex or not. If you have a set you have some properties over the sets that you can prove the set is convex. If this set is convex, the function that we use it for this epigraph is convex. And if the function is convex, the set is also convex.
So epigraph is a part of the function, part of the convex function.
It's this area above the function. They have a Johnson inequality again. The basic one is that if the function of theta x plus 1 minus theta is less than theta f x plus 1 minus theta f y, it was the basic one, and we have the extension of that for the expected value of the z. If the z is the random variable, the function of the random expected value of the z is less than expected value of the f, and if we talk in the discrete domain, the probability of the z is equal to x is equal to theta, and z equal to y is 1 minus theta. And it means if we have a function and the function is convex, and we have we don't have exact input of the function if we have distribution of the function, and we use for example the expected value of the input. The expected value of the input is less than the expected value of the input of the function. It's okay. And next topic is some operation that preserve the convexity. I think I have some examples that I'm going to solve it, but let's go a little through the operation of the that preserve the convexity, and then I will back again to some examples, and I try to solve some of the examples to at least help me to understand what's the topic. Okay, here again we have three ways that we can say some function is convex or not. The first one is the simple definition that we use. This definition for proof, for example, why the maximum is convex. And the second one is the Hessian of the function, and that we used for the I forgot the name. For quadratic over linear function x squared over y, we use this property, and now we have a new operations that it can preserve the convexity. It's the first one is positive weighted sum and composition with the affine function. Then non-negative multiplication. Non-negative multiplication preserve the convexity. For example, if is for f convex, if we multiply by a positive value, it will be convex. The summation of the function is convex. This summation means if we have an integral of the functions, it's convex. If we have the expected value of the function, it's convex. And composition with the affine function, ax plus b is affine. If we have the function of the affine function, the result is convex. Here is one example of log barrier function. And log array function is the summation of the log bi minus alpha transpose x, and this function is convex because we can assume that this one is some affine function, and the log function, the summation of the minus log is the because log is a concave, and summation, if we have a minus of the concave is convex, and the summation preserves the convexity, and the result is convex. Any norm is convex because the norm is convex function, and ax plus b is affine, and some convex affine function is convex. And the second one is pointwise maximum. If we have a function f1 through fn, their function, they are convex. Then the function, if we define a new function f of x that is the maximum of this function, the result is convex. It means if you have a we have we have two functions, and okay, maybe my drawing is not. I'm going to have the same domain, and the max function is this function, and if these two functions are convex, if these two functions are convex, the maximum of the function is convex. For example, if we have a piecewise linear function f of x, which is maximum over I for all aix plus bi, this function is convex.
Excuse me, I get, okay, this one is one function, this one is another function. So we just want the maximum.
Maximum.
For the both of them.
Yes, maximum of the
So
function.
it says that if the maximum of the.
If each of these functions are convex, there is
maximum. Okay.
if you have a concave function, there is some situation that is not convex. Do you need some example?
No. And how about the minimum? The minimum has the same.
For the minimum, we have some condition. For the maximum, there is no condition. But for the minimum, if we want to find the minimum of the some convex function, I think it's in the slide. The domain of the function is supposed to be convex. If the domain is convex, minimum of the function is convex. But I need to double check. I think it's in the slides. Maybe 4 or 5 slides. And some of the large component of the x in Rn, if we have a function, it's and we want to sum the, for example, 5 or 10 maximum coefficient of that, it's convex. Yeah, and I think there's some short proof for that. The max of this, if we have this sequence of the indexes, the max of this one is convex. pointwise supremum or pointwise maximum. It means if you have a function which is convex jointly over x and y. Sorry, the function is convex over x for each of the y's. Therefore, the maximum or supremum of the function for the all y's are a convex function. There's some examples here, and I have some that I will work on that. Let's go to the next one, which is a very important operation. If we have a function f of x, which is h of g of x, the function is convex if we have some conditions. If we have some chain of the functions, if we try to find the first derivation of the function, without considering that the function is derivative is differentiable or not, the first x is equal and if we do again the derivation, we will have this one double square of the g prime multiple to h double prime of gx plus h prime of gx g double prime of x. And for finding the its function or the function of f is convex or not, we the only thing that we can do is the easiest way is to find this derivation is positive or positive semi-definite. As you can see here, we have some a square function, which is this one is the positive. We want to have this one positive. Therefore, the double prime of h it's supposed to be positive if we want to have the convex function. Therefore, if the h of x itself is convex plus the g of x, if it's convex, the h prime is supposed to be positive. It means h is supposed to be increasing or non-decreasing. If the g of x is convex, h is supposed to be non-decreasing. It's the first one. G of x is convex, h is convex from here, and the h is non-decreasing to keep this term positive. If g of x is concave, if g of x is convex, it means this term is negative. If this term is negative, we want to have the whole thing positive. We know h of x is convex, therefore this term is positive. This one is negative, and we want something negative here to multiply to the negative one and create something positive. Therefore, h is supposed to be decreasing or non-increasing. And we can have a different combination of this convex, concave, increasing, non-increasing, non-decreasing. For example, if we want to have a function that is concave, if we want to have f is concave, if we want to have f to be the concave, we need to have two negative terms here. This term is positive, therefore h supposed to be negative. Therefore, H for having this one, H supposed to be concave. If H is concave, this term is negative, and we want to make sure that this term also is negative. For having this term negative, we have two ways. This one negative, or this one positive, positive or negative. In the first option, if the h of x is non-decreasing, means this term is positive, and let me write that here as a non-decreasing. If h is non-decreasing, g is supposed to be concave. Okay. And if the h of x, I don't want to write it down, this one. If h of x is negative, which means is non-decreasing, non-increasing, it's decreasing, the g can be convex, and the result of f is concave. Okay, and one important thing here is h tilde. If you remember, we talked about the extended value. Yes, extended value extension. If we have a convex function, the extended value of the function, for example, if you remember, I drew a picture something like this, and it has this domain. This is the original function f, and f tilde is this function. Here is plus infinity, and here is plus infinity. And the definition for the non-increasing and non-decreasing, we talking about the extended value extension. It means if we have a quadratic function, something like this, and it starts from 0 to plus infinity, if we use the extended value expansion, this function is not it's not increasing, because we have a plus infinity here, and we have some decreasing some part of the function. In the 0 we have we dropped, and we come down to the 0, and again start to increase. Therefore, if we have this function, we have to define, for example, between 0 to minus infinity is equal to 0, which means this function. Yes. This function is increasing, and it's as a condition for the question, because I have some example that I want to solve, or I can do 2 or 3 examples very fast to, okay. Okay, we have let's the example is from for the chapter 3 of the optimization book, and it's some of them is for the beginning of the chapter. For example, f of the x, it's equal to max of 1 over 2 x2, and this is max of the some function that we define that the maximum of the function is the convex, and this function is convex. Also, you can draw the picture and see it's convex or not. The next example is, for example, f of is cosine hyperbolic of x, which is equal to e power x plus e minus x over 2, and this function is convex or not? Any idea? The exponential of the function is convex function, and we have an operation that says summation of the function is convex, and we multiply with some positive numbers. This will preserve the convexity, and this function is convex. Next one is the same function. It's a log concave or not. It means if we calculate this value and we define the function f1 of x, which is equal to log of how about this function? Okay, this function is concave. You can do the chain rule, and if you do the chain rule, it's a concave function. Or you can do the derivation. You can do the definition, but the hardest one is use the definition because it's a little hard. Log of this function is x minus x minus log of 2.
No, it's not multiple. Multiple of
Okay.
the x.
It is not a good way to prove it.
It's minus x.
Okay.
It's okay, you have the rule you just show like in the previous slide.
Yeah.
You have the scalar composition rule.
Yes. Okay, and let's and the last example, I think we talked about the negative entropy. It was f of x equal to x log of x. If we do the derivation of this function, is equal to log of x x over x here we define the I think in the bottom I have a absolute value. need to have the plus or minus x. And this term is positive, and this term is positive. Yes, because this one is positive. In any case, it's zero or something positive. Therefore, the second derivation of this function is positive, and this function is convex. For the next meeting, I will review fast this material, and I will continue the operation that preserves the convexity.